Thank you, Rilem Youth Council, for giving me an opportunity to present my research. Today, my research topic is potentiality of lithium slag as a sustainable pozzolan in the development of low carbon concrete. I am SM Arifur Rahman, PhD candidate in Curtin University. First, I'll discuss a brief introduction of my research. Cement is an indispensable component in the concrete industry, and the production process have heavy micronizing and calcination, which requires huge energy. Researchers using optimized proportion of pozzolan sourced from different waste streams as a partial replacement of cement to put an energy cutoff for the cement production and global carbon footprint. Lithium slag composed of silicon, aluminum, and calcium and iron, making it an excellent candidate for supplementary cementitious material. Researchers are using lithium slag without calcination and micronization, as its amorphous aluminosilicate phase provides a remarkable advantage to enhance the pozzolanic activity. In Western Australia, discrete number of lithium mining sites have open pit extraction system, and after lithium purification, lithium slag is generated, and this is currently disposed as backfill. The material characterization of lithium slag will provide vital understanding for the experimental design, reaction kinetics, hydration product formation. Here we can see silica alumina sulfate concentration of lithium slag are higher compared to cement. On the other hand, calcium, magnesium, and iron are lagged in lithium slag. The median particle size of lithium slag is 38 micrometer, 2 times than the cement, and the specific gravity is 2.46. The grain size and volume distribution curve show that roughly 5.8% of the total volume incorporated by 100 micrometer lithium slag particles. The quantitative XRD of the cement showed 64% alloyed and 1.9% Portlandite, which can induce 13.7 pH in 100 ml DI water, while lithium slag retained 31.6% amorphousness as 22 to 29 degree of 2 theta angle in the diffraction pattern and mostly contains light metals, lithium, sodium, magnesium, and sulfur in the amorphous phase, other than calcium, aluminum, and silicon. Therefore, using lithium slag as a pozzolan may provide amorphous intermediate hydration product compared to crystalline calcium silicate hydrate alone. This characteristic composition helps to induce long-term strength development in the pozzolan cement composite system. Here, the lithium slag was analyzed in transmission electron microscopy, and the dark field image shows the variable contrast indicated that lithium slag contains cenospheres, which is hollow geometry that increase the internal surface area of the pozzolan and helps to hold gel and capillary pore of water for the strength development in the long-term hydration. The EDS indicate the amorphous aluminosilicate crystal for the position 1 and basanite for the position 2 as the prismatic shape. We considered electric conductivity and unsaturated live conduction as the precursor test. The left side of the beaker showed that the ion dissolution in DI water from the pozzolan and increases with time. The middle one showed the dispersed calcium ion in DI water and is of fixed concentration. Combination of both systems induce the hydration product formation gradually with time, and the calcium concentration reduces along with the conductivity. LS is lithium slag is highly efficient in consuming 19.4% lithium in 1 day, followed by 88.9% lime removal at 28 days, fulfills the requirement of British Standard 8615. Little calcium oxide concentration increased at 28 days due to atmospheric carbon dioxide precipitation to form calcium carbonate by reacting with calcium hydroxide. Lithium slag in DI water raise approximately 1500 microsiemens centimeter at 120 second, that is in 2 minutes in DI water. At 236 hour, the electric conductivity was reduced by 51.9% to the initial, followed by 2.6% increase till 56 days. So EC in DI water was slightly decreased after 1100 hour, and this may be due to the adsorption of heavy metal ions on the pozzolan surface. This can be explained from the microstructural section. Most researchers have found that 10 to 20% cement replacement by lithium slag is feasible. This study was challenging as high volume supplementary cementitious material increase the unknown phases, specifically lithium slag increases the sulfo-illuminate phases. Earlier, pozzolanic activity was calculated from oxide composition and state activity index only. The previous studies left an opportunity to focus on the chemical test to assess the lithium slag pozzolanic activity and hydration products. So cement-based pozzolanic activity test includes fraternity strength activity index R3 test, where cement was partially replaced from 10 to 60% in weight proportion. Water requirement in making mortar is determined from the flow of the control mortar plus minus 5 millimeter. In fraternity test, the test data above the curve indicate the non-pozzolanic system, while below is pozzolanic. Here, the calcium concentration of 10 to 60% lithium slag incorporated mixes rapidly decreased, and the formation of hydration product contribute available calcium. As a result, all mix become pozzolanic at 3 days. Therefore, fraternity test fails to characterize high volume pozzolan cement composites. However, the test continued to understand the relative decrease of calcium concentration, as shown in the top left. This was very helpful in the characterization of the activation time for the lithium slag mixer. It is seen that 10 to 60% lithium slag was not activated in 1 to 3 days, but increased its efficiency to remove calcium ion in 3 to 7 days. And the reaction stabilized at 7 to 28 days. The compressive strength of the control and 40% LS was roughly 64 megapascal and 62 megapascal at 90 days. It is seen that 50% lithium slag incorporated mix is still satisfied the requirement set by ASTM for 75% SAI at 7 days and 28 days, British standard at 85% at 28 and 90 days, and Rilem 65 SAI at 28 days. The amount of heat released in earth heaters is related to the formation of hydration product and bound water. Firstly, a high heat burst was observed within 15 to 20 minutes of the mixing of the dry material in the alkaline water due to the wetting and dissolution of water followed by a dormant period. Secondly, the formation of the ettringite is induced in the dormant period at 3 to 4 hours due to the dissolution of the reactive sulfate and aluminate and carbonate ions. Thirdly, the dormant phase is accelerated by the amorphous silicate phases of the pozzolan to form calcium silicate hydrate at 20 to 22 hours. And then the deacceleration phase. In this study, the primary hydration peaks of 30 to 60% lithium slag are slightly delayed compared to the 10 to 20%. The increased aluminate provided early false setting by combining with all available silicate and calcium ion, while the excess sulfate at this stage could not react to form ettringite as C3A phase of the cement reduced with the partial replacement. Therefore, the secondary hydration peak reduced with the reduction of cement, and the susceptibility of internal sulfate attack was highly reduced at high replacement of cement. The diffraction peak of the lime reacted lithium slag at 1, 3, 7, and 56 days were analyzed for the crystalline phases of the hydration product, shown in left. Here the ionic phases determined in the cobalt K alpha radiation, and the formation of ettringite calcium silicate hydrate at 10.61 and 34.15 were analyzed as shown in right. The formation of the ettringite and calcium silicate hydrate degrade with time as the sorry, reactive light metals may incorporate to form amorphous and amorphous intermediate hydrogen products. The amorphous and amorphous intermediate hydrogen products were analyzed in STM-EDS. The peaks were analyzed at 137 and 28 days for the same XRD samples. The peaks are analyzed and the probable hydrogen products are summarized here. At 1 and 3 days, ettringite, secondary ettringite, and sodium and aluminum based calcium silicate hydrate was formed. This indicated the premature hydrated gel initially expands and forms gel and capillary pores. At 7 and 56 days, stable hydration products with potassium, magnesium, aluminum, iron, and sodium-based calcium silicate hydrate formed with ettringite and secondary ettringites. These hydration products are amorphous intermediate and forms within the gel or capillary pores to strengthen the microstructure of the lithium slag cement composites. The increase in the electric conductivity and decrease in the calcium oxide concentration at long-term hydration is um, due to the precipitation of iron to form iron-based calcium silicate hydrate in the solution. The Pozzolan requirement for lithium slag also satisfied the ASTM, BS, and Australian standard Pozzolan requirement. Here we can see that the sulfate was higher, but it still will not pose internal sulfate attack threat because the C3A phase of the cement has been decreased with the increase of the partial replacement of cement. The loss of ignition has been increased 7.8%, which has been increased from the BS and AS standard, but within the ASTM standard. The particle size are a little bit coarse, 45 micron, which is higher than the requirement for the ASTM and BS standard. Other than these parameters, the strength, activity, and water requirement and the oxide requirement are fine with all standard requirements. And it is seen that 40% lithium slag incorporated cement mixes provided good strength and good development in strength. So the 7, 28, and 90 days strength activity index of the specimen are plotted with R3 test data, and we can see a good correlation on the right side with 0.60 to 0.72, where the Rilem considered 52 Pozzolans to find out the same R square value and found 0.83. In conclusion, I'd like to summarize that 40% lithium slag as a supplementary cementitious material could react with 79% calcium oxide of cement proportion and provided 93% strength activity index at 28 days and produced 53.1 joule per gram SCM hydration heat at 7 days. Also, the lithium slag provided amorphous aluminosilicate phases of hydration product by using sodium, magnesium, aluminum, and potassium and iron ions in the calcium silicate hydrated structure. The physiochemical and compressive strength properties of lithium slag as a pozzolan met all the standard requirement, and lithium slag is a competitive SCM from the R square value is already confirmed. This is my LinkedIn profile and this is my Google Scholar profile. You can stay tuned for the update. Thanks for a lot for your kind attention.